Finally, let's look at how we quantify the effect of agonists and antagonists. So the underlying theory for all these interactions is the so-called receptor occupancy model, which basically um, interprets the activity of drugs at receptors as based on the binding of the ligand to the receptor. And so the action of a drug will be proportional to the number of the receptors occupied by that drug at equilibrium. And so in this theory, the magnitude of the response is directly proportional to the amount of drug bound, and so maximum response is elicited once all the receptors in a cell or tissue are occupied at equilibrium. And this is somewhat a simplistic way of thinking of things, but basically links the response to a log dose of either agonists or antagonists. And by doing that, we obtain um, a nice sigmoidal curve, which gives us the same quantities or equivalent quantities that we have seen before, where EC50 is the concentration of drug that elicits 50% of the response, of the maximum response. So according to this theory, homeopathy really makes no sense because homeopathy is based on infinite dilution of the drug, and so we'll be right here where no the receptor is occupied, and therefore we will have no action. In practice, how is this measured? Well, it's measured by assays, biological assays that are pretty simple. And so in this case, we are looking at a contraction of pig ileum. So we literally take a piece of the pig ileum, we string it up to two cantilevers, and then we measure the strength of the contraction by measuring the force applied to these two cantilevers. And so we'll have a percent of maximum response, where maximum response is when all the receptors on the ileum are occupied, and so we have maximum contraction. This is what happens when we have acetylcholine as ligand. That's the natural ligand for the muscarinic receptor. And so we'll have a certain EC50. Now we are trying to evaluate the efficacy of another agonist called propionyl-choline. And what we see here is that now the EC50 is much larger. It's actually 1.5 order of magnitudes larger. So this agonist is less potent because it requires a higher concentration of the drug to elicit the same response, but it has the same efficacy as acetylcholine because at saturation we obtain the same contraction. So another situation that we can have where the agonist we are evaluating is less potent and has less efficacy. For example, if we compare the action of oxycodone with nefopam, so those are two painkillers, and in this case our y-axis is somewhat less quantitative because it's simply the percent of patients with complete pain relief, and so that's somewhat subjective. But nevertheless, we can still build these dose response curves. And what we find is that in this case, again, the EC50 for oxycodone is much higher than the EC50, lower rather. So oxycodone is active at smaller concentration than nifopam. But importantly, besides the loss in potency, we also have a loss in efficacy because even at saturation, the patients that report complete pain relief is only pretty small. It's about 20%. So let's look at the summary of possible dose responses for agonists. So we have several situations possible. We have a full agonist, which elicits 100% of the response. We have partial agonists which elicit only part of the response, and this can be done though with the same efficacy, with the same potency. So the EC50 may be pretty high. Then we have neutral antagonists, but basically conserve the basal activity of the receptor, but do not really increase or decrease the activity. And then we have inverse agonists, which basically inhibit the response of the receptor to the natural ligand. And so the net effect is actually the opposite activity. So what we had at 0 here was really the constitutive activity of the receptor in the absence of ligand, and this is what we have instead in the presence of our inverse agonists. So let's look at the same dose response curves for antagonists. Then what we do is basically look at a curve, dose response curve for an agonist, and see how much this curve is moved to the right in the presence of a given concentration of antagonists. This is true for competitive antagonists, right? So what we'll have is that with a competitive antagonist, the overall efficacy will be the same. However, the potency will change. And so we can build a family of these curves at different concentration of antagonists. Another situation that we can have in where the antagonist is irreversible, and so the effect of the antagonist is really to kill or disable the receptor. So we'll have a change in efficacy. Whereas the potency will stay the same because what the irreversible antagonist is doing is simply diminishing the concentration of the receptors available. So the EC50 will be the same, right? It's just that, what 50 is will change. Okay, so oftentimes receptors are redundant. So we have already seen that the receptor for acetylcholine is actually formed by two very different families. And the way this was dissected is by looking at reaction of certain tissues in the presence of two natural alkaloids, nicotine and muscarine. And so what was found is that nicotine will be an agonist on certain receptors in certain tissues, whereas muscarine will be an agonist in other tissues and will have two completely different responses. And so we'll discuss that in due time when we talk about acetylcholine and related drugs. But for now, what I want you to remember is that while nature utilizes often the same neurotransmitter for different receptors, and it can do that because basically it obtains specificity in the response by where the receptor is, so what tissue we're talking about. In the lab, we have to be a little more selective, and so the different structure between the nicotinic receptor, which is an ion channel, and the muscarinic receptor, which is a G protein coupled receptor, was actually discovered by observing the different response to different receptors. How does acetylcholine act on two different receptors? Well, what has been found is that, in fact, this is due to the flexibility of the conformation of acetylcholine. And so different receptors bind to different conformations of acetylcholine. So for example, the anti-periplanar conformation, which happens to be the most stable conformation, acts on the nicotinic receptor, but not on the muscarinic receptor.